Hello everyone, this is Gourango Charan. I would like to present our paper towards real-world 6G drone communication, position and camera-aided beam prediction. This work is done in collaboration with my colleagues from the Wireless Intelligence Lab at Arizona State University and supervised by Dr. Ahmed Al-Khadib. This work is supported by the National Science Foundation. Drones are envisioned to form the basic building block of next-generation aerial networks and are the key to enable futuristic applications such as extending the coverage of millimeter wave wireless networks and supporting latency-critical applications, enhancing the capabilities of security monitoring systems, precision agriculture, and unmanned delivery, to name a few. To support these future applications, there are three main requirements: high data rate, ultra reliability, and extremely low latency. However, it is quite challenging to simultaneously meet these demands. In order to meet the high data rate requirement of these future applications, the drones will need to be equipped with millimeter wave transceivers. Millimeter wave and sub-terahertz communication with their large bandwidth have the potential to support multi-gigabits per second communication. However, the wireless communication in these bands primarily suffer from high attenuation loss, resulting in a low signal-to-noise ratio. To overcome these challenges, the systems need to deploy large antenna arrays and use narrow beams at both transmitters and receivers to guarantee sufficient receive SNR. Nonetheless, beam management in millimeter wave drones is challenging. Given the large antenna arrays of the millimeter wave communication system, selecting the optimal beams is typically associated with large training overhead that scales with the number of antennas. And the highly mobile nature of the user necessitates a frequent update to the optimal beam index, which further increases this overhead. Furthermore, the three-dimensional motion of the drone results in frequent changes to the optimal beam index, which requires recurrent fine-tuning. This motivates looking for new approaches to overcome this beam training overhead in millimeter wave drones. Developing solutions for the millimeter wave beam training and channel estimation overhead has attracted considerable interest over the last decade. These solutions can broadly be divided into two subcategories. The first subcategory consists of the classical approaches. These solutions have generally focused on constructing adaptive beam codebooks, designing novel compressive sensing techniques, and leveraging the channel sparsity. These classical approaches, however, can typically save only one order of magnitude in the training overhead, which is not sufficient for large antenna array systems and high mobility applications. These challenges further motivated the development of machine learning based approaches that can learn to leverage side information such as wireless receive signature, user position, and visual data to predict the optimal beam indices. Although this prior work have shown great potential, they are primarily based on synthetic datasets and focused on scenarios with humans and vehicles as the transmitter, where the users typically move in an easy-to-predict mobility patterns in 2 dimensions. Therefore, these solutions might not scale to real-world scenarios with millimeter wave drones. In this work, we primarily focus on the sensing-aided approach. In particular, we propose a deep learning-based sensing-aided solution to reduce the beam training overhead in millimeter wave drone communication. Next, we first highlight the motivation behind utilizing sensing-aided solutions. In wireless communication, the current and future channels are functions of the terminal positions, mobility patterns, and the various elements of the surrounding environment. In general, it is hard to characterize this channel function analytically. Now, if we have enough features that represent these variables, we can derive or learn how to map these variables to channel attributes. This is where machine learning models and additional side information can be utilized to learn this mapping explicitly. To do so, we first need to capture these features from the wireless environment. Sensing modalities such as vision, user position, LiDAR, radar, etc. can efficiently capture these features from the wireless environment. Developing efficient solutions for sensing-aided beam prediction and accurately evaluating them requires the availability of a large-scale real-world dataset. With this motivation, we built the DeepSense 6G dataset. DeepSense 6G is the first large-scale real-world dataset with coexisting communication and multimodal sensory data such as vision, GPS data, LiDAR, and radar collected in realistic wireless environments. The goal of this dataset is to enable a wide range of applications in communications, sensing, and localization. The DeepSense dataset consists of multiple scenarios collected at different locations, different times of the day to incorporate diversity. The scenarios focus on different use cases such as vehicle to infrastructure communication, drone communication, reconfigurable intelligent surfaces, among others. The figure here shows a data collection testbed used in one of the scenarios. An important question that arises now is, why do we need multimodal data? In this work, we propose to utilize visual and positional data to predict the optimal beam indices. This is primarily motivated by the low cost and ease of integration to the existing infrastructure. Further, the recent advancement in machine learning and computer vision has enabled new capabilities such as accurate object detection, image segmentation, localization, to name a few. However, each of these sensing modalities has its own limitations. For example, practical positioning sensors do not normally provide accurate positions for narrow beam alignment. Similarly, the visual or camera data is sensitive to lighting and weather conditions. All this highlights that unlike synthetic data, real data is not perfect. In this work, we compared the beam prediction performance of the different sensing modalities and present their advantages and limitations. In the next few slides, we present the proposed solution, development dataset used for evaluating the solution, and the beam prediction performance achieved by the proposed approaches. First, we will present the key idea and formulate the sensing-aided beam prediction problem. In general, the mechanism of directing the narrow beams can be viewed as focusing the signal into a particular direction in space. The beam vectors divide the scene into multiple sectors where each sector is associated with a particular beam value. Therefore, given a predefined codebook, the beam prediction task can be transformed into a classification task where, depending on the location of the user in the visual scene, a beam index from the codebook can be assigned. Now, the next question is, how will the system operate in real world? The assumption here is that at every frame, the base station will capture the following data points, which consist of visual data and the beam training result. The position data is either fed back by the user or derived from infrastructure-based positioning. The primary objective of this task is to utilize the available sensory data and predict the optimal beam indices from a predefined codebook. For this, we define a prediction function psi theta that maps the input sensory data to the optimal beam index. In this work, we adopt a machine learning model to learn this prediction function. Next, we present the proposed machine learning based solutions. The proposed solution utilizes visual and position data to predict the optimal beam indices in millimeter wave drones. The proposed vision-aided solution adopts the ImageNet pre-trained ResNet 50 model to perform this classification task. The model is further modified by removing the last layer and replacing it with a fully connected layer of size M, where M is the total number of beams in the predefined codebook. The model is then trained end-to-end in a supervised fashion with a labeled dataset. For the position-aided beam prediction, we utilize the normalized latitude and longitude information along with the height and distance of the drone to predict the optimal beams. For this, we design a feed-forward neural network with two hidden layers. Given the low complexity of the input data itself, the final machine learning model only has around 60,000 parameters, which is a significant reduction from the vision-based approach with more than 23 million parameters. Next, we present the DeepSense 6G scenario utilized for this work. To evaluate the efficacy of the proposed solution, we adopt scenario 23 from the DeepSense 6G dataset. The figures present the two different units of the data collection testbed. It highlights the different components of the millimeter wave drone acting as the transmitter and the base station acting as the receiver. This scenario consists of diverse wireless, visual, and position data as shown in the example image samples. The details of the testbed and the final development dataset is presented next. The testbed consists of a mobile drone acting as the transmitter and a stationary base station. The drone is equipped with a 60 GHz quasi-omni antenna and is capable of capturing real-time position data. The base station receiver has a 16-element 60 GHz phased array adopting a beamforming codebook with 64 beams. It is further equipped with an RGB camera that captures images of the wireless environment. The initial data collected using the testbed is referred to as the raw data. This raw data further undergoes a post-processing pipeline that involves data modality synchronization and filtering. The resulting development dataset consists of around 12,000 samples. The data is further divided into training and validation sets following a split of 70-30. Next, we present the performance of the proposed solution on this development dataset. We first evaluate the beam prediction accuracy of the proposed sensing-aided solution. This figure shows the top K beam prediction accuracies of the different approaches. The top K accuracy is defined as the percentage of the test samples whose ground truth beam index lies in the predicted top K beams. Among the four approaches, vision-aided solution achieves the best beam prediction accuracy. The position-based solution has the lowest performance. This is mainly because of the inherent error in position data collected by practical GPS sensors. They are not accurate enough for narrow beam prediction. Also, by using position information alone, the model is not aware of the height and distance of the drone from the base station. As we further incorporate this information, the top 1 beam prediction accuracy of the model improves by almost 15% as shown here. We next investigate the impact of height and speed on beam prediction accuracy. For each analysis, we divide the test set into 3 subgroups based on the height and speed of the drone. As shown in the top right figure, the ML-based solutions makes the most mistake in prediction when the drone is flying low. For the speed-based analysis, as shown in the bottom right plot, we observe that there is limited impact of higher speed on vision-aided solution. Also, there is a slight drop in performance for higher traveling speeds of the drone. With the interesting results, I would like to summarize by highlighting 3 key points. The first is that we believe that proaction and awareness are great enablers for future wireless networks. The overall performance of the proposed model enforces our hypothesis that additional sensory data like RGB images and position of the millimeter wave drones can be utilized to predict the optimal beam indices and more. The results further highlight the need for multimodal sensing data and efficient fusion strategies. This is primarily to develop robust and accurate solutions by overcoming the inherent limitations of the different sensing modalities. Thank you very much for watching. If you have any questions, please feel free to get in touch with us.